AP Physics 2, 2016, number 3. In this diagram, well, this is some background information on the diagram you were given, because the diagram you were given is one that we haven't spent a whole lot of time on. What we've spent a lot of time on are these electric field diagrams. Like, for example, the basic electric field for a proton are these blue lines. Those are the lines of force. That's what we've drawn. And if you have an electron here, they're all inward. So we're very familiar with these diagrams, these electric field lines for positive, negative, and parallel plates. For parallel plates, the electric field lines, they are these blue lines. They always go from positive to negative. That's our convention. And they're equally spaced, and they result in constant forces, and they can accelerate protons or electrons. They accelerate protons to the left and electrons to the right. So those are some things we're familiar with. What we're not as familiar with, even though we've mentioned it once, but it's been a while, are these like dashed lines, which are the lines that are on the next diagram, the diagram on the actual question. So I'm just giving you some background here. They're called lines of equal potential. And once again, potential is not voltage. Voltage is when you change from a location. So for example, in this problem right here, if I'm at this location right here, which is 90 volts, and a good thing to keep in mind is that volts are joules per coulomb. If I go from this location right here to this location right here, my energy increases. A volt is a joule per coulomb. So let's say the difference between these two isopotentials, equal potentials, anywhere on this curve right here, this circle, is 90 volts, 90 joules per coulomb. It's also very similar, like holding a book up in the air at the same level. It has the same gravitational potential energy. But anyways, in this case, though, if I move from here to here, I have more energy. If I move a positive charge from here to here, because it doesn't want to go that way, it takes work for me to do that. And let's say the difference here is 10 volts. So this goes now, it goes to 100 volts. This would be 100 volts, 100 joules per coulomb, because it takes work for me to, it's kind of like pushing a dart into a gun. I have to push hard. I have to do work. I have to add energy from an external source to increase the energy or to put the positive charge closer. So this might go to 100, 110, 120, 130, 140, 150. So the energy increases as you get closer and closer and closer to that positive charge. Same thing over here, though. All right. Actually, this one's kind of the opposite. I'm going from 90. I'm lowering the energy from, say, 90 to 80 to 70 to 60 to 50 to 40, 30, 20, 10, and 0 energy over here, 0 joules per coulomb, as you go across this particular electric field. Once again, those are isopotentials. We've actually had problems like this on the WISE test before with particles that we move around from one plate to another plate. So that's where we've seen that at least once before as on a WISE test, these equipotential lines. So, and other things that go along with that is, like, if I put a proton here, it has the electric potential energy, 90 joules per coulomb of charge I put there. So if I know how much charge I put there, say it's just one proton, I could take that 90 joules per coulomb, multiply that by the 1.60 times 10 to the negative 19th coulombs, and it'll tell you how much potential energy it has. That will then be transferred into kinetic energy. That's a type of problem that we've done in the past. If I let that proton fly across here, it'll have kinetic energy of that amount, conservation of energy, transfer of energy when it hits this plate over here, and then it'll have 0 joules of potential energy. But then it gets complicated. Once again, we've seen these diagrams before, especially this diagram here. This is these solid blue lines. The solid blue lines are the electric field. It's the direction, say, a positive particle would more or less follow. If you put a positive particle right here, it would more or less go like this and get sucked in over there, and so forth. This is the field for two like charges. If they had two negatives here, it'd be the same diagram, except for the arrows would reverse, and all these dashed lines would be the same. So once again, like here, if I have 90 joules per coulomb, if I get closer to a positive, that energy goes up, 90, 100, and these might not be 10 volts, they might be 5 volts. So it might be 90, 95, 100. So the spacing is somewhat arbitrary. Over here is 90. So for example, if this is 90, I just made that up, I made them all 90s, 90 joules per coulomb. If I go to the left here, this iso line, if I go by tens again, if that's what the spacing is here, this would be less energy, be 80, 70, 60, 50, 40, 30, 20, 10, and then 0 energy when I get right close to that negative charge. And then the energy would go up as I go to the right, 90, 100, 110, 120, 130, 140. So those isopotentials, on any one of those dashed lines, it'd be the same energy per coulomb, which you could calculate the energy once again if you knew what kind of charge you had there along any of those lines. And they're very similar to maps, geographic maps, landscape maps that have lines of elevation. So, for example, on what I was trying to say is topographical map. A topographical map where, for example, if this were a map, these would like the elevations like 100 feet, okay? These would be like 100 feet, and then you're going uphill, it'd be 100 feet. Well, let's say this is 90 feet. This would be 100 feet, 110. You're going uphill. Each of these lines represents an elevation. So along here, that's what your elevation is, 90 feet. Then you go uphill. So these lines of elevation show you that you're going uphill. So this would be going uphill when you get up there, or if you go this way and go uphill. So every, once again, somewhat arbitrary. These might go by 10 feet, or might go by 20 feet, or by 30 feet, depending on what the map scale is. And over here, you're at a certain elevation, and this would be going downhill. You go from 90 feet to 80 feet to 70 feet. So that's the analogy for a topographical map. They're going to ask about that in the question. So here's the actual problem with some of the givens. Well, I think all the givens. This is a 50-volt potential here, not a potential difference. This is the potential difference, 10 volts. That's the change in potential as you go from one isopotential to the next isopotential. So 50 volts here. I do not like the units volts. If you think about it, a volt is a joule per coulomb. That might help you here. That's an energy level. 50 joules of energy per coulomb of charge anywhere on this curve. That's how much energy you have. And the thing is, everything's by convention is for positive. So if I have a positive charge here, it has 50 joules of energy per coulomb. So if it's 1 coulomb, it would have 50 joules of energy. If it was 2 coulombs, it would have 100 joules of energy. But anyways, 50 joules per coulomb of energy for a positive charge. Well, if this center spot is a positive charge, which it says it is, it's important here. If I take a positive and move it closer to another positive, that takes work on my part. It also increases the energy. It's like lifting a book or going uphill. So this has to be more energy here. The closer you get to the positive charge with another positive charge, the more energy it is. It's also kind of like pushing a dart into a dart gun. More energy the closer you get. So the change in potential here is 10, potential difference. Sometimes we call that voltage. So if that's 50, then this would be 60, because they told us the change is 10, and then 70, then 80. So based on that, so from 50, that's 60. That's why A is 60 volts, and 80 is and B is 80 volts. And you don't need to put the plus in there. It's assumed it's positive. If it were negative, you'd put the negative on there. But those would be the points for that part. So in part BI, if you think about the first diagrams I gave you on the first page, these two charges must have the same sign because, for the reasons I've written down here, and it's kind of like, on a topographical map, it's like having two hills, where this is a big wide hill, this is really steep, small, I mean, they're at the same height. Those spots, X and Y, are at the same height. Because if you follow these isopotentials, this is 50, 60, 70, that's 70, so there's 70 joules of energy. So in both cases, I'm making the argument that as you go closer, you're getting more energy. 50, 60, 70, 80, 90, 100 joules, 100 joules per coulomb. If you get to that spot over here, so if you're getting more energy for both diagrams, for both points, X and Y, they both must have the same charge. This must be positive as well, just because the energy is increasing, and I made that argument down here for B sub I. Then you have to come up with the magnitude. Which one has a stronger charge? Well, if you look at the potential equation for a point charge, KQ over R, for a given distance, all right, or for a given potential. For example, that inner circle there for both of these, the smallest circle here and the smallest circle here. The smaller circle here has a point C on it, has a bigger distance. But that circle here with a C on it has the same potential. It's 100 volts. Both diagrams, that inner circle is 100 volts. So to have the same potential at those locations, for a bigger radius, you must have a bigger charge. In point Y, there's a bigger radius. So point Y, or charge Y, has to be a bigger charge because you have a bigger distance for the same energy level. And that's the argument I'm making right down here. So this is, once again, kind of a difficult question relating this to gravity and gravitational fields. So if these are two masses now, this is a mass and this is a mass, how do these relate to gravitational fields and gravitational potential? Well, here's the gravitational potential energy equation. And I'm making the argument that, kind of the same argument, that for a given central mass, this must have the larger mass, because if you look at the energy level here on that circle C, kind of like I was making the argument for electric potential in the past question, to have the same amount of energy at point C here as you do in a smaller circle over here, the central mass here, Y, has to be a larger mass to get the same amount of energy, or it maintains more energy at a greater distance. So the gravitational field must be stronger. Or maybe another way to say that here, when I'm referring to a second mass, I'm not talking about these two masses compared to each other. Let's say, basically, I'm kind of like talking about a third mass. In other words, if I look at this guy over here, and this is a really small distance, if I drew that size circle over here, that really tiny circle that I have circling around X, that tiny circle would have more energy because this circle with the C on it has the same amount of energy per mass, same potential as this little circle. So those are equal in energy levels. This circle here, it's a bigger radius. So if I kept going with smaller and smaller circles here, so if I had a given circle of the same size as this little circle, isopotential energy, gravitational potential, would have way more energy than this one. So in other words, if you look at the equation, if I then made that new circle and thought of a third mass and put it on that little circle over here, it'd have way more energy. That's the argument I'm making right here. At a given distance from both X and Y, draw a little circle here, there'd be way more energy here for that little circle than for this little isopotential circle. So now they're asking you to put a proton at point B and describe one similarity and one difference between the electric and gravitational forces exerted on a proton. So it helps, I think, in this case, to look at the two equations for force. This is Newton's law of universal gravity, Coulomb's law of attraction or repulsion between electric charges. And in this case, you can see, or we know, that both forces are proportional to 1 over r squared. The other way you could have said that, you could have said the forces are inversely proportional to r squared. So you could have said it that way, but this means the same thing. So that's how they're similar. But what's different is, if the proton is there, gravity will attract it to the system, mostly towards Y. Electrically, point Y, a sphere is positive, and the proton's positive, it'll be repelled. So that's how they're different. Gravity will attract, electrical force will repel. So now we're at part D, and once again, the temptation here, because they give you numbers, is to do this numerically, but they ask you to do it symbolically. So I kind of don't like the way they asked that question. That's another reason why this question, I think, wasn't asked in the best way, and it's a very convoluted problem in a sense. I mean, there's a lot of good concepts here, and it's really not that hard if you do it symbolically, but you got to be really careful because the temptation is to do it numerically, because you know that the charge of a proton is 1.60 times 10 to the negative 19, so you could actually start calculating these numbers, but it's actually faster just to do it symbolically. In part I, if you just look at the equation, potential difference, delta V equals delta U over Q, and just basically plug in, and don't use the 20. It's there, it's tempting to use, but if you rearrange this equation, delta U equals delta VQ, and delta V, if you move from your initial location, potential at B, to potential at A, the change in potential or change in anything is always your final value, your delta, your V sub A, final potential, minus the initial potential times Q. So that's the answer to part I. And then double I, you want to figure out the work done in terms of those symbols. So here we go. Work is the average force times the distance, even though the force is not constant. They're saying to take the average force or the average field. Well, by definition, E equals F over Q. Average electric field strength equals the average force over your charge. So if you take this equation, solve for force average, F equals EQ, and we've used that a lot between parallel plates and so forth to do uniform acceleration problems for protons between parallel plates, but we're not doing that here. But this equation helps out because, well, work is F times D, and in this case, the angle is in the same direction as the motion, so we're kind of ignoring the cosine of theta here. You could talk about that, but that's extra work. But bottom line, you're just plugging in E average times Q for D, and you get this equation. I'm sorry, you're plugging this in for F, for force, not for D. D is still there. So there's your answer. So it's a lot faster without plugging the numbers in, but it's a little deceptive because you're going to want to maybe try to do some calculations that will not be graded. So that's the answer there. And finally, the last part here, I think they asked you to do way too much in this problem, but let's just learn something here. So they have two students talking about this system and making statements. So which student, or are they correct? Well, it turns out they're both correct. So that's a little tricky. Student 1 is correct because basically they're referring to the law of conservation of energy, kinetic energy being transferred from potential energy. And student 2 is also correct. If you look at the work equals force times distance, kind of the problem we just did in the previous step. And because the force is applied to the same direction as motion, the student is doing work, or not the student, but the electric force is doing work as it speeds the proton up. And so therefore the direction's in the same direction as, the force is in the same direction as the motion, so work is positive.